So suppose that we're interested in finding an asymptotic expression for this function of n. Remember the way that it works. First thing, everybody to the exponent. So it's going to be e to the minus x log n plus n log x dx. All right? Now, we're going to do a Taylor series expansion of the exponent centered at its maximum value. So, I need to give it a name just so that I can indicate what I'm doing. All right? Just like that. We're looking for the maximum value. So we're going to set the derivative equal to 0. Our maximum will take place when x is equal to n divided by the natural logarithm of n. Now we effect a Taylor series expansion. So this will be minus n divided by the natural log of n times the natural log of n is going to give me n. Plus n times the natural log of n divided by the natural log of n. Okay? Plus the first derivative at the maximum value times x minus the maximum value. The first derivative is 0, so I don't need to write that part. Plus 1 over 2 factorial, the second derivative, evaluated at the maximum value. So that's going to be minus 1 over 2 n divided by n over log n squared. Times x minus n divided by natural log n, all squared. Now remember, we truncate the Taylor series expansion at the quadratic term, expanding about the maximum value. All right? To get the asymptotic expression, that's what we do. We simply truncate the expansion completely. We substitute this into the exponent. So that gives us integral 0 to infinity e to the minus n plus n natural log n divided by natural log n minus, all right, let's see what we got here, log squared n over 2n times x minus n divided by log n all squared dx. This part is constant. He goes out front. E to the minus n plus n, natural log n divided by natural log n. My gosh. Times. All right. Here I was integrating from 0 to infinity. I'm going to write that out, even though it's going to cause me to run out of space. All right? Now, this is almost a Gaussian integral. But I'm integrating from 0 to infinity instead of negative infinity to infinity. But when x equals 0, this is e to the minus, and then it's going to be n squared over log squared n. So this has the value e to the minus n over 2 when x is 0. For large n, that's very small. So we say this is approximately the integral from negative infinity to infinity. Essentially what we're saying is I'm supposed to be integrating this, and instead I integrate this. This extra piece is expected to not make a large contribution. We will still have essentially the same value. It'll just be much easier for us to work with. And that's what we're going for. Remember, the point of an asymptotic expression is not to get something that's exact. It's to get something that's close and easy to manipulate. All right? So, we have approximately e to the minus n plus n times the natural log of n divided by the natural log of n times, this is e to the minus alpha u squared, square root pi over alpha. So it's going to be the square root of 2 pi n divided by the natural logarithm of n. Now, of course, at this stage, in essentially any calculation, we want to check our work. So let's go ahead and do that. I need you to understand that especially when working with these asymptotic expressions, we cannot always trust that Mathematica is giving us the correct result. So we need to sort of sneak up. All right? So, here is our function. I'm going to make a numerical value of it, and I'm doing n to the minus x, x to the n, from x equals 0 to infinity. Now, I need to give it an n. So I'm going to do over dot. So slash period is interpreted by Mathematica as replace. I want to replace n with, let's do 8. All right, and I'm going to do this to 10 digits. All right, and there, it gives me 55.46258. Now I'm going to use my asymptotic expression. E to the minus n plus n log, of n divided by log n. All right, times square root of 2 pi n divided by log n all squared. All right, and let's do that also to 10 digits. Oh, I didn't tell it what n was. Great. Remember, replace all. All right, so we got 54.888 versus 55.462. Remember, this is an asymptotic expression. It is supposed to be better when n is larger. So let's check it for n equals 10. 376 versus 373. What about n equals 100? Now I've got 9.598 times 10 to the 90. 9.59 times 10 to the 90. All right, so relatively speaking, it's doing a pretty good job. Now, we do have to worry when we get very large. Here's n is 1,000, 2.68 times 10 to the 1,727. Let's see what ours gives. 2.68 times 10 to the 1,727. Now, this one was a well-behaved example. It didn't get so big that Mathematica complained when it did the numerical integral. That will not always be the case. Mathematica will sometimes complain. When it complains, you should read that as maybe you're not trustworthy anymore. Okay? So you want to sort of sneak up on the larger values. If the asymptotic expression is getting better and better and better, and then suddenly the numerical estimate from Mathematica is off by a factor of 10 or 300, it's a sign that the asymptotic expression is more trustworthy than Mathematica's numerical evaluation.